Hi everyone, welcome to the latest in the Water Security Alliance series of webinars. It's a series that features a guest speaker each week and is aimed at stimulating discussion and knowledge exchange between academics, researchers, water professionals and students. These seminars are hybrid when possible, but they're always accessible via Zoom. So you can register at Eventbrite and you can view past seminars at the Water Security Alliance website. If you're a member of the Water Security Alliance ECR community and interested in chairing a session, you can contact us on wsainfo@cardiff.ac.uk. For this talk, we're delighted to welcome Dr. Brett Snider. Brett is a postdoctoral research fellow at the University of Exeter. His research interests focus on the digital transition facing water utilities throughout the world. And the title of this discussion is Designing Water Distribution System Anomaly Detection to Reduce Search Areas. So over to you, Brett.
Yeah, and this research is funded largely by two EU projects, which is the Aqua 3S and Firewire for Water. So just the overview of what today's talk is going to be about. I'm just going to give a brief introduction highlighting the issues that are being faced in some of these water systems currently, and specifically with the 21st century, and provide an anomaly detection overview, which is seen as one major tool that can help address some of these problems. And then I will discuss specifically my research into locating and detecting anomalies in water distribution systems, and specifically the application of the maximum coverage location problem in improving the localization of the event. A case study is used to describe the issue and explore the results and concluding next steps. So as many of you guys who are coming to this presentation are probably well aware, there's a multitude of issues facing water systems in the 21st century. First off, I think one of the major ones is the aging infrastructure. This is something that my PhD research was largely on, and for what's probably well known is that many of these water systems and the infrastructure for these systems have been built over many, many decades. And the long life of these systems often causes them to be buried and forgotten. And so the replacement of these systems aren't keeping pace with the age of the systems. And we're coming to a point now where a large percentage of these pipes or whatever infrastructure under the ground is needing to be replaced. And as they're beginning to deteriorate, a lot of these systems are starting to fail more frequently. There's been one study in North America that was focused on pipe breaks specifically, and it suggests that in North America overall, pipe breaks have increased by 27% in recent years, I think between a 6-year period. And so that's 27% increase is significant. It can impact water utility operation, but also impact the end users and possibly lead to contaminants entering the system. So that's just one factor facing many utilities. The other, obviously, is climate change. And so if we think about climate change, it really impacts every possible stage in the water cycle and how it impacts for urban systems. If you think from a supply side, reservoir and management of water becomes a lot more difficult with climate change variability. We see in more prolonged droughts or more aggressive droughts, for example, in California, as well as South Africa a while back had the issue with possibly leaving day zero where they didn't have any water to supply their infrastructure. The other thing, if we start to go down the line, it impacts everything. So climate change is also impacting customer demand cycles, making it more difficult for the water utility operators to predict and provide adequate value or water to the customers. And then if we keep even further going down, it starts to impact treatment plant design and stormwater management, and et cetera. And then lastly, I think one of the major ones I'd like to point out is the impact of urban migration. So perhaps many areas population growth isn't as aggressive as much anymore. But what is happening still is a large urban migration. So more and more people are starting to move to these big urban areas. And these systems that were already in place for decades are already near capacity. And they're having to cope with these large influx of people, putting more demand on the system, making it very difficult. And so these are just some of the issues being faced by many water systems throughout the world. And there's a variety of solutions, but one of the key solution is considered the digital transition. And so here what we're talking about is a digital overview or adaptation by water utilities to improve system resiliency with some of these new challenges. And so this digital transition can include a variety of things, such as digital twins, remote sensors and IoT agents, and AI software to help manage these systems and plan for future resilience. However, the digital transition will ultimately lead to an influx of data that can overwhelm many of these utilities that aren't familiar and used to dealing with this type of data. And so therefore, careful consideration must be thought of how these tools are implemented to help manage this influx of data and provide an easy to interpret actions for utility staff. And so that's just the quick overview of some of the issues facing water systems in general. The remaining focus of this presentation is more on the development of one of these tools that are involved in the digital transition, not specifically anomaly detection, focusing on the end user to improve water distribution system resiliency. So as the digital transition of water systems continue, one key thing that's probably going to happen for most systems is the implementation of remote sensors. And these remote sensors are going to become more and more common, and handling the data generated by these sensors is going to be very difficult for many of these utilities. It's unpractical or impractical for water utility operators to analyze the data generated by these sensors as it's produced. Therefore, tools are going to be needed that can analyze this data and detect anomalies within the data, and then using that information to notify the staff of a possible issue. So these anomaly detection algorithms or models must be flexible and able to encompass a wide range of data and data formats in order to detect the various anomalies that might be occurring within the water system, as well within drinking water systems, as well as other water related systems. So with this in mind, we've started to develop an anomaly detection model that is able to detect and locate anomalies across a wide range of sensors and water systems. And so here's a general overview of one of the models that we've developed. And so here you can see there's three key separate models. There's a historic anomaly detection, EPA net anomaly detection, and EPA net anomaly localization. So just a quick kind of discussion on these is that the historical anomaly detection focuses on sensors that are not aided by water distribution system modeling. And so not aided by EPA net or hydraulic modeling. And so this model, the historical anomaly detection, can be used for a variety of systems, not just water distribution systems, but can also be used for flooding or et cetera, depending on the types of sensors that are in place. And so how it works is it looks at the data that is a numeric type of data, and looks at the patterns to try to identify when an anomaly might be occurring based on typical values. And when that occurs, an anomaly alert is triggered. Although it's numeric data, it can work with a bunch of data as long as it's converted into a numeric form. So if you think about it, categorical data or text data could be converted into a numeric form. For example, we are currently working on integrating the number of tweets with regard to a possible water event to be analyzed by this methodology. And so if there's a large number of tweets regarding a certain area or a certain water system, then an anomaly is triggered and it is notified to the appropriate staff. The next two models, the EPANet anomaly detection and EPANet anomaly localization models, are developed specifically for water distribution systems to detect and locate anomalies. So these models follow a model-driven approach. So it uses the hydraulic model to calibrate it and to perform scenarios that you wouldn't want to perform in real life, being able to model and then calibrate the sensors or the anomaly detection to appropriately identify these anomalies. And so if we went into, it would take probably a while to discuss each model separately. Instead, I'm going to be focusing on specifically the anomaly localization model and how it's been developed to improve specifically the utility's ability to send out search crews to detect the event that has been triggered by the anomaly detection model. So detecting an anomaly by analyzing data from a sensor is not too difficult. And the big key problem is, though, once you've detected the anomaly, is what do you do about it and where do you go to identify it and shut it down? And so since water distribution systems are very, very large and these sensors can be costly, implementing these sensors at every possible junction or location is unlikely and impractical. And so what we need to do is develop a model that is able to use a small number of sensors spaced out throughout the water distribution system to locate the actual anomaly. Once the anomaly is located, then a search crew can be sent out to confirm the location and repair it and react to the event much quicker. So when developing an anomaly localization model, you need to think about, and this is for any of these tools that are being implemented with the digital transition, is that you need to think about how it's going to be used by the utility and especially the end user. And so the vast majority of the localization model, so there's the localization models, there's been a fair bit of research in it in recent years, but the vast majority of these models focus on identifying an exact location, either by predicting a node within the distribution system that the event is occurring at. So that would be a typical classification model, or predicting location coordinates that minimize the distance to the event. And these would be regression models. However, once an event is detected and located, an anomaly crew or a crew must still be sent out by the utility to confirm its location and either isolate and repair it if necessary. If this event isn't occurring directly at this location that was predicted by the models, the crews are then left often to search the nearby area without any specific guidance from the predicted model. So therefore, it's very important that we, instead of just predicting an exact location, that we predict a general search area for the crews that can identify the event with much higher probability in reducing the search area for the utility. So to be able to predict a search area instead of a specific node or XY coordinates, this kind of changes the problem, and it must have a unique solution. And to the best of my knowledge, this hasn't really been explored that much in literature yet. So my contribution, or our contribution to this kind of research is looking at the maximum coverage location problem. And so here, what we're really searching for is a way to identify a specific area that covers the largest probability of the event locations. And so here we can use the machine learning classifier to predict the probability of the event occurring at each node within the water distribution system, and then apply this maximum coverage location problem algorithm to identify the ideal search area. And so the maximum coverage location problem has been around for a very long time. It was invented by Church and Reval in 1974, but it has gained a lot more attention in recent years because of advances in geographical databases and coverage searches. A good example of this problem would be if you think of cell phone towers, and we're trying to, let's say a company is able to place 2 cell phone towers and they want to maximize the number of customers that it's going to reach. So a list of possible cell phone towers are provided, their range is given, their ability to cover the demand, and then the geographical location of the customer demand is provided as well. The maximum coverage location problem algorithm then searches through those possible search areas to maximize the demand covered given a range of the coverage. And so this can be easily adopted to the anomaly localization model approach, and this is how we adopted it by doing the same kind of methodology. So here we have the machine learning model predicting the node probability. So every node within the network has a probability of the event occurring at it. And so if we look at these blue dots, that would represent the probability. And so the larger blue dots would represent a higher probability of the event occurring at that location. And then we have a possible search area center. So here I've only put in 6, but we would develop an entire grid to search through. And then the search radius is customizable for the utility as well as the number of search areas that they would prefer to have. And then the model searches through and identifies the 2 search areas centers that are maximize the coverage. The one point here is that these 2 points, even though they're double covered, wouldn't be counted twice. It would be the total area of this circle or of this double circle. So using the maximum coverage location problem, the anomaly localization methodology is developed here where a random forest machine learning model is calibrated by simulating events within the EPANet hydraulic model. And then the machine learning model classifier predicts the probability score of the event occurring at each node within the network. And then the maximum coverage location problem analyzes the grid search based on the utility's preference. And the output of the ideal search locations is provided. And so here's just a quick kind of an example. And if we're looking into it, the main thing is that you simulate a normal scenario to calibrate what is typical readings for the normal sensors. Again, adding noise into the demand to fluctuate to make it more realistic, as well as adding noise to the sensor since the sensor is going to have some inaccuracies. Then we simulate the event at possible locations at nodes or at pipes throughout the network. And then again, adding demand and sensor noise to it and calculating the Z score or the residual, comparing it to the normal event. Then using these readings, we can train a machine learning model, which in this case, we've trained a random forest model. And then the model then with new readings outputs the node probabilities, and then the maximum coverage location problem with the user's defined settings. If they want 2 search areas, 3 search areas, they want the radius to be a certain amount, outputs the desired search locations. So to make sure that this approach it works, we analyzed it using a case study. So here, this is an example of a network. This is in EPANet, again, that we've used. And we simulated 13 sensors throughout this network, seven flow and 6 pressure sensors. The total network is about 25 kilometers. Again, this is a skeletonized graph, and this is typically the case for water systems. So not every single service connection or et cetera is on there. But this is why it's important, because although the leak could occur anywhere throughout it, the search area would encompass it even if we simulated it at a specific node. And then the overall geographical area is 12 kilometers squared. And for the test set, so an independent test set, we ran 100 leak scenarios throughout the network. Oh, and those leak scenarios were obviously random, occurring at random times and random spots throughout the network. So the first thing we wanted to do is to provide a sensitivity analysis on the maximum coverage location parameter values. So specifically here, we're looking at the grid spacing. So as I mentioned before, we wanted to generate a large number of possible locations of the search area or the center of the search areas. And so here the grid size, we generate a grid. And so as the grid size becomes larger, the spacing between them, these centers become larger. Therefore, less search areas are analyzed, but the accuracy decreases. So here you can see the accuracy slowly tends to decrease. Here we can see the number of leaks detected in the test database. But here we also compare it with the computation time. So obviously, if there's a lot less search areas to analyze, the computation time decreases as well. So this just highlights that there's going to be needed a trade-off between computation and accuracy. And so this is something that the utility will have to analyze to figure out what that trade-off is preferred for their scenarios. So the next thing that we analyzed is the search radius. And so here, the larger the search radius, the larger the search area, and therefore much more likely to include the event or the leak in this case. So here you can see as the search radius increases, the leaks located increases as well. Again, this is a thing that needs to be set by the utility for their specific preference. For example, some utilities may be able to search a 50-meter radius or 100-meter diameter in a certain amount of time that they are comfortable with in detecting the anomaly or locating the anomaly. So based on their preference in location times, we can develop search radiuses to match that preference. And then using this information, if we still wanted to have a higher degree of accuracy, we would predict more search areas. And so that's the next analysis. So as we increase the number of search areas, obviously, again, the number of leaks are going to, leaks correctly identified or located will increase as well. But this is kind of just highlighting the customizability of the maximum coverage location problem and how it benefits the utility, because their ability to have maybe 2 or 3 or 4 crews sent out to locate this event as quickly as possible allows them to predict more search areas. The other thing to mention here is that these search areas also have the probability of the event covered. So you can prioritize which search area you go to first if you don't have the same number of crews at search areas. And so last kind of analysis here, and probably the most important, is looking at comparing the maximum coverage location problem approach that we developed with other leading anomaly location models. And here we want to determine if the maximum coverage location problem actually reduces the search area required. And so here we analyzed specifically the search area in meters squared needed to capture 50% of the leaks simulated in the test data set. And so we did this comparison across several models. Here, first a random forest classification model. And so here the random forest classification model selects a specific node with the highest probability of the event occurring at. And so from that output of that highest node probability, we expand the search area. So this is what would happen in a typical case. The utility would go to that node and then it would search, expanding out circular to find the leak. And so here we did that and kept expanding it out until it covered the leak for 50% of the scenarios. And then that's the search area. The next model here is a regression model. So a random forest, again, but using regression to predict the XY coordinates, minimizing the geographical distance to the actual node. So here again, we expand so that it predicts an XY coordinate and we expand outwards until 50% of the leaks are captured within the test data set. And then the third one that we compared is somewhat similar to the maximum coverage location problem, where the classification output has all probabilities of the nodes occurring, and then using a clustering algorithm, a hierarchical clustering algorithm with a set max distance to determine 2 search areas. So you couldn't do this with a 1 search area; it would have to be 2 or more. But we developed that approach to analyze if just providing a clustering methodology after classification, if that improves it greater than the maximum coverage approach. And so what you can see here is that and then I compared it to 1 search area and 2 search area for the maximum coverage location approach, so our approach. And so what you can see here is that the maximum coverage location approach results in the smallest search area. So if we're using 1 search area, the search area space is reduced by 35% compared to regression, and even greater, almost 50% compared to the classification approach. And then if we're using 2 search areas, this impact is even greater, at around 80% compared to regression, and still about 35% better than the hierarchical model. And so these reductions in search areas could be considered equivalent to reductions in average search time. So if you think about it, suggesting so that if we adopted the maximum coverage location approach, we may be able to react 35 to 80% quicker in confirming the actual leak or any type of water quality or event in this case. And so by identifying this, we can significantly minimize the impact, or react quicker and minimize the impact on the customers and other nearby infrastructure. So I think we'll just quickly end it here, but just some concluding statements. I think as more water utilities begin to embark on this digital transition, data influx is going to be a big issue, and handling this data is going to be very difficult. And so any tools that can make this data interpreted easier or streamline this approach is going to be extremely important, with the key that we're focusing on the utilities end use here is going to be very important. This presentation in particular focused on a very specific tool, the Anomaly Localization, and tried to highlight the important aspect that search crews, even with a very accurate model, search crews are still going to be needed to sent out to confirm the location of the event and react appropriately. So therefore, to reduce the crew's search time, we need to look at it as reducing the search area. And so the maximum coverage location approach is used and to predict the specific search area. And then analyzing this approach compared to the other models has shown that the maximum coverage solution significantly reduces the search area, benefiting the utility and the customers significantly. The other thing about this approach that's really useful is the customizability of the maximum coverage solution. And so here we can highlight the fact that different utilities are going to have different requirements, have different crews available, different search areas that they're able to perform. And so having a very customizable solution is something that's very important. Overall, the maximum coverage location problem localization model that we've analyzed here is just one example of how the digital tools that focus on water utilities will be crucial for handling some of the challenges in the 21st century. I think these digital tools will be very important, but need to be designed with utilities end use in mind to help speed up this digital transition and have more buy-in. I think there's a variety of research, future research with this kind of model. One thing that we're considering is looking at a heuristic genetic algorithm to help improve the maximum coverage location problem grid search. So as we were mentioned before, if we have a very, very large grid search, it has to search through every single one of those grids or center points to see if that's the ideal search area. And so if we use a genetic algorithm here, we can reduce that computational time and hopefully improve the accuracy as well. And then lastly, I think the next step for us is to integrate this localization model into an intervention management model. And so here what we're talking about is, so once a event is detected by the anomaly detection model, it is located by the anomaly localization model. It is then, scenarios are then analyzed to see what is the most effective way of minimizing the impact on the customers and on the utility. So having a variety of performance, we've already started to develop this, and having a variety of performance indicators that evaluate these decisions, we can start to see which valves should be closed, which pressure settings should maybe be adjusted, should we implement overflow or overland bypass pipes, etc. And so these are a variety of the options that we can analyze, and then by analyzing this, inform the utility and most effective decision. And so with that, I think I'll end it there. Hopefully it wasn't too dry, and hopefully you guys have some questions. Thank you.